This is the video presentation for Chapter 12, Below Grade Construction. Let's talk about the parts of a structure. There are three parts. Any building is going to consist of the superstructure, which is that part of the building that is above ground level. The substructure, which would be the basements, if there are any basements, and the foundation system, and that's the structure that lies below the substructure. And if the basement doesn't exist, then the building only has two parts, the superstructure and the foundations. And here we see it graphically. So let's talk about the foundations. There are two types, shallow and deep. The shallow foundation is going to extend only a short distance below the surface of the ground, and it's going to bear directly on the soil. And usually we find this in low to mid-rise buildings. The deep foundations are going to be used where I have soil of adequate strength, but it's not available close enough to the surface to allow me to use a shallow foundation. So here I'm going to be either using piles or piers, and these are generally used for high-rise buildings. Now, the choice of whether I use a shallow or a deep foundation is going to depend upon the quality of the soil closest to the surface. Now, some commonly used materials are going to be reinforced concrete, either with standard reinforcing steel or post-tensioning tendons, or reinforced concrete masonry, basically concrete masonry units. Less commonly used are going to be plain unreinforced concrete, unreinforced masonry, and preservative-treated lumber and plywood. The book tends to limit discussion to concrete with rebar or post-tensioned and reinforced masonry. So let's discuss some shallow foundations. There are two types of shallow foundations. There are foundations that consist of footings or monolithic concrete foundations, which are under the building's entire footprint. If I talk about foundation systems using footings, these are going to be footings that are under the perimeter foundation walls and interior piers, basically short columns, with an elevated ground floor. There might be footings under columns and load-bearing walls with a concrete slab on ground, or there might be isolated column footings with or without a basement. And again, graphically, this is the foundation system with an above-ground floor, isolated concrete footings for columns or piers. Here is the slab on grade, and here is the isolated column footings. When I'm dealing with shallow foundations based on footings, I have two types of footings. I have the continuous footing, otherwise known as a strip footing, and it's usually used where the superimposed loads are linear, basically a load-bearing wall. Then there are independent footings or isolated footings, and these are used where the load is going to be a point load, such as a column. Now here, the bearing capacity that's required under a column footing is usually higher than that for a wall footing because of the concentrated load on the column. Sometimes, with a steel column, they may use a stepped footing or a pedestal to save concrete. If you recall from print reading and the brick veneer building, here is a continuous footing, and here is an isolated footing. A combined footing will combine two isolated column footings. Usually I have two or more adjacent columns that are closely spaced, heavily loaded, by combining them into one footing reduces my excavation. There's that cost factor again, and we'll distribute the load over a larger area. Or it might be used where an exterior column is right on the property line or adjacent to an existing building, and I cannot build my normal isolated footing. Two alternatives to a combined footing are going to be a strap footing or a cantilevered footing, basically using a cantilevered grade beam between the two isolated column footings. So here are the commonly used types: the continuous or strip footing, the isolated column footing. The isolated column footing with a pedestal, it increases the footing strength without increasing the size of the amount of the concrete. This is a combined footing. Here, the combined footing, notice the property line is here, and I cannot extend the footing past this point. Here is a strap footing where I have a grade beam that connects the two, or the cantilevered footing. The strap beam will restrain the tendency of the footers to overturn by connecting them to an adjacent footing. When we're talking about monolithic concrete bases as a shallow foundation, these cover the entire footprint of the building, and we have three types: the slab on grade, the mat foundation, or the raft or floating foundation. The slab on grade is the most common type of foundation system. It is low cost. It has our friendly ease of construction, and usually it's used for low-rise, light-frame buildings, single-family homes, multi-family homes, motels, professional offices. It will function as the foundation system and also the ground floor of the building. It might be a reinforced concrete slab or post-tensioned. A mat foundation, on the other hand, all the columns and the walls in the building will bear on one thick reinforced concrete slab. Here it's used where I have low bearing capacity of the soil, even if it's deep below the surface. So independent column footings become so large that I've pretty much excavated the entire area. So if the excavation required for isolated footers in a building is more than 50%, it's usually more economical to use the mat foundation. It's also used where the bedrock is so deep that using a deep foundation system such as drilled piles and piers is uneconomical. So because of the large depth of a mat foundation, it's sufficiently rigid to distribute the loads from individual columns on the underlying soil. So here's a slab on grade foundation. Here is a mat foundation, and you can see it is a very large monolithic structure with individual columns. Now the raft foundation or floating foundation is a hollow mat, and it's formed by a grid of thick reinforced concrete walls between two thick reinforced concrete slabs. The soil that is excavated for the foundation is usually equal to the weight of the entire building, so that I am unchanging the pressure on the soil, and so the building is essentially floating on the soil. And again, graphic for a raft foundation. This foundation here is replacing the soil equal to the weight of the entire building. So as far as the soil is concerned, we haven't really added anything to it. So let's talk about deep foundations now. Deep foundation systems will include piles or drilled piers, which are basically slender columns that are buried in the ground. Because they are slender, like anything else, long and slender, it is prone to buckling, but the soil around them will prevent them from doing that. It's that it provides the lateral restraint. And the load is transferred either to bedrock or to soil of a higher bearing capacity. Piles can be made of steel, timber, or concrete. Usually they're driven into the ground, except for concrete piles, which are usually site cast. And if they're site cast, they will be called a drilled pier or a caisson. The material that gets used is going to depend upon availability, cost, soil, environment, load, installation equipment. So here is, again, graphic, pile, and a pile cap. What this does is if I have multiple piles, I put a cap over it that allows the load to be distributed evenly to all the different piles. Here's the use of grade beams and a reinforced concrete slab on drilled piers. So, making use of piles as a deep foundation. Usually I'm going to have steel and concrete under heavier loads. Wood piles have limited load-bearing capacity, basically because of the nature of the material, and limitations on the cross-sectional areas of the tree trunks. I can only get a wood pile of a particular size because there are fewer big trees out there. So there are two ways that piles will support the loads. There's a friction pile that supports the load basically through the friction, the contact friction created between the pile itself and the surrounding soil. So these piles are tapered to a narrow cross section at the bottom to facilitate driving, not unlike a nail. If they're tip bearing or end bearing, they will transfer the load to whatever the pile is resting on and do not depend on friction soil. They will be smaller in cross section than drilled piers, and they will be installed in groups. The steel piles might be H-shaped or hollow pipes. The hollow pipes are then filled with concrete after they are driven. Steel piles are going to be covered with protective coating if they are used in corrosive environments. Concrete piles are usually precast, solid. They can be attacked by sulfur, so we have to use sulfur-resistant Portland cement, type 4. They may have a steel tip to prevent the concrete from being damaged as the concrete piles are driven into the ground. If wood piles are used, they are usually treated with creosote or chromated copper arsenate, CCA, as a preservative. And here's a picture of some former steel piles along the Cuyahoga Valley Scenic Railroad of a bridge that was probably built in the 1880s and was since replaced, but the piles were cut off at the water line. Here are other piles This is the Fitzwater Road Bridge that I had showed you earlier, and you can see the remains of piles from an earlier bridge across the Cuyahoga. When piles are being installed, they're usually driven in by a pile driver. And here are the piles that were being driven in for the abutment of the Fitzwater Road Bridge that I was just showing you. Friction pile uses the friction between the pile itself and the soil. End bearing, we are either on bedrock or a soil of a higher bearing capacity than above it. The multiple piles with a cap might be very similar to a long footing. Drilled piers. They can be as large as needed. And when I drill a pier, my alignment is certain, as opposed to driving in a pile. Think of it more as you drill a hole, putting in a screw, as opposed to driving in a nail and hoping it goes in straight. Drill piers can be friction or end bearing. If they are bearing on rock, they may be socketed. So here is an end reaction pier, end bearing on a surface. Here's a belled pier relying upon friction of the soil, but with a bell at the end so that it becomes more difficult for this to be withdrawn because I have the pressure of the soil on this end piece. Or if it's an end bearing, they may drill part way into the rock or higher bearing capacity soil, and that is called a socketed pier. Expansive soil is going to create an uplift as it swells, so we have to have stable soil of sufficient depth to offset that uplift of the drilled pier. Here's the auger that would be used for drilling a pier. Rebar cage is set in the hole once it's drilled. And again, a tremie is used to deliver concrete to fill up the pier. And this is very similar to the bentonite slurry piles that were used to keep the walls from collapsing that we talked about in chapter 11. Steel casing might be used for a drilled pier. Normally they might be used if the pier is very deep or there's the possibility of soil caving in. They will be extracted as the concrete is installed. They might also be used to prevent water entering where we have water-bearing soils, where we're below the groundwater line. But they will be spun into rock because rock doesn't contain water, and then they'll have the water removed. When the pier is going to support another member, we'll have rebar coming out so that it can connect to whatever the above ground member is. So piles can be suited for marine and coastal sites. Drilled piers would not be suitable because there is water present, there might be a high water table, or we have sandy soil with a cave-in potential. The advantage of piles is that they can be used immediately. We do not have to wait for the concrete to cure. And piers, drilled piers, might be good for a low-rise, inexpansive soil. Pile driving is noisy and requires heavier equipment, so a drilled pier, would be a more suitable alternative because we really don't want to tick off the neighbors. Piers can be used in urban locations. Again, vibrations and noise. They can support a larger load than a pile. They do not require to be capped. And the technology, however, for piers is less complex. Again, there's that trade-off with cost, more skilled labor, and those areas. Piers can be more economical and, again, suitable in expansive soils. So let's talk about a case study here, Terminal Tower. It sits on bedrock. And in 1926, 16 caissons were driven down 200 to 250 feet to the bedrock. Now remember that caissons is another word for drilled piers. And the idea was to avoid unnecessary vibrations to the building as the trains entered the station from below. And here's a picture of the drill piers being put in place from 1926. And that ends part 1 of chapter 12. Please continue now with part 2.